So, hello everyone again. This is lecture 6 part 1 of semiconductor electronics materials devices and simple circuits. In this lecture we will understand the full wave rectifier concept and then we can move forward with the further concepts. So, let us not waste any time, let us start our discussion only directly. So, I am Sameer Levankar, let us begin our discussion. So, right now we are on the 7th topic, that is the application of junction diodes as a rectifier. In this concept, what are the things which we understood? First of all, the thing which we understood was called as your half wave rectifier. So, what was basically half wave rectifier? Half wave rectifier is basically used, let us say that this is the input AC voltage given to us. Then the output voltage is being obtained is like this. Okay. Similarly, we were on the introductory part of understanding the another concept, that is full wave rectifier. So, in full wave rectifier what is happening? Let us say this is the again input AC voltage being given. So, this will be the output voltage. Fine. So, that thing being said, let us understand the full wave rectifier from the discussion we left in the previous part of the last lecture. Okay. So, let us start the discussion directly. So, application of a junction diode as a rectifier. Okay. So, this was based upon your half wave rectifier concept. So, this is the circuit for a half wave rectifier. Let us move on directly to the full wave rectifier. So, this is the input for your half wave rectifier basically, that as you can see that it for the reverse biasing the voltage obtained is 0. Fine. So, this was the concept which we were trying to understand. Okay. So, we were done till this point. So, basically what was happening till this point was, what was happening was ki in the opposite, in the upward part it was positive, and if it is positive in this part, it is negative in this part. The voltage is negative in this direction, that means that it is forward bias in this case, and it is reverse bias in this case. Correct, it is forward bias in this case, it is reverse bias in this case. Then next thing which we understood is, so now this was till the first cycle. Okay, so this was the first cycle, and therefore finally what we got was this cycle. Fine. Okay, so what is actually happening? What is the cycle which is working here? So this is the cycle which is working on the diode A. Similarly, what is the cycle which is working in this second waveform, that is at B. So this is the cycle which is working here. Okay, so as you can see that the polarity of even the cycle is reversed here. Okay, so this is the waveform at A and this is the waveform at B. Therefore, for the first cycle, what is happening? This is getting added up. This is getting forward. This is forward bias. This is reverse bias, and hence you get this as the answer. Similarly, for the second case, this is reverse bias. This is forward bias, and therefore this you get this as an answer. Okay. Similarly, this is your forward bias. This is your reverse bias, and therefore this you get as an answer. Okay. So next, in the next cycle again, as you can see that the waveform at A was again your reverse biased, and at waveform at B it was your forward biased. Therefore finally you get the answer as this. Okay. So if you see the diagram also clearly, it is written there that it is due to D1 diode 1, it is due to D1 diode 1, but this time this is due to diode 2 and this time it is due to diode 2. Okay. Fine. So let us read again. So from the fifth point, it says that in the course of the AC cycle, when the voltage at A becomes negative, in the course of AC cycle, when the voltage at A becomes negative with respect to the center tap. So, everything we are saying with respect to center tap here. Okay. The voltage at B would be positive. So, this time this would be positive and the diode 1 will be negative. Okay. So, in this part of the cycle, diode D1 would not conduct. Why it would not conduct? Because this will be in reverse biasing. Okay. But diode D2 would. So, therefore, this will be forward biasing. Okay, giving an output current and output voltage across RL. Okay, so it gives an output current and output voltage across RL, which is being obtained like this. Fine. Next thing is thus we get output voltage during both the positive as well as negative half of the cycle. Okay, so therefore, what we got output voltage for this half of the cycle also, and we got the output voltage for this half of the cycle also, and the cycle then continues. Then this is the periodic only. So, hence we keep on getting waves. So, thus we get the output voltage during both the positive as well as the negative half of the cycle. Okay, so obviously there is a more efficient circuit for getting rectified voltage or current than the half wave rectifier. Okay, so basically now what we can say that we have some more efficient device or more efficient circuit which is being performed, which can do the rectification of the complete circuit. In the half wave rectifier, what was happening, that only a half wave was being rectified. In the case of your full wave rectifier, the complete circuit is being rectified, and hence this is more efficient or more usable. Okay, so that is only being written here. So, obviously this is a more efficient circuit for getting rectified voltage or current than the half wave rectifier. The rectified voltage is in the form of pulses of the shape of half sinusoids. Okay, so the rectified voltage is in the form of pulses. As you can see clearly that what is the rectified voltage? It is on the pulses and half sinusoid. So, this is the form of a half sinusoid. Okay, this is a full sinusoid, this is a half sinusoid, or like this is a full sinusoid and this is a half sinusoid. Okay. So, as you can see clearly that this is in the form of your half sinusoids. Okay. So, though it is unidirectional, it does not have a steady value. Okay. So, though it is unidirectional, it does not have a steady value. So, because even though it is always on the positive direction only, but the value is keep on varying. So, it is not a steady value. Fine. So, now to get a steady DC output, now what we require is we require a constant value, So, now we will do some of the more inputs in this and try to find out a constant value here. So, to get a constant steady DC output from the pulsating voltage, normally a capacitor is connected. So, as you can see, a capacitor is connected. So, the concept of your full wave rectifier and half wave rectifier is over. Now, we are trying to understand a different topic here. Okay. So, to get a steady DC output from the pulsating voltage, normally a capacitor is connected. As you can see, a capacitor is connected across the output terminals, So, which are the output terminals? This is one of the output terminal here, or let us say this is the output terminal here and this is the output terminal here, parallel to the load RL. So, as you can see, this is parallel to the load RL. So, one can also use an inductor in series with RL for the same purpose. So, either you can use a capacitor which is parallel to your RL, or you can use an inductor which is in series with your RL. Okay. So, this inductor and the capacitor concepts are being, I think you have dealt with, because this is the last chapter of your physics. So, you understand completely what is a capacitor, what is the definition of capacitor, how are the capacitor being used, what is the basic principle behind capacitor, what is an inductor, what is basically inductance, what is self inductance, what is mutual inductance, etc. Okay. So, those all concepts are of different concepts. So, we will not go into detailing of that. I hope you know these concepts. Even if you do not know, you can just refer back to those chapters regarding electric charge, capacitance and the current, electricity, or this inductor is basically about your mutual inductance. So, basically this would be found in electromagnetic induction. Okay. So, that being said, let us move on to the third point. So, since these additional circuits appear to filter out of the AC ripple and give a pure DC voltage, so they are called as filters. So, what does it mean basically? That let us say we add an input voltage here. So, if we add an input voltage here, finally what is the output with capacitor input filter? This is the output. So, you can see that this is almost a DC, this is almost a steady voltage which we are obtaining. Okay. So, as you can see clearly, what is AC? After AC we added a rectifier. What did the rectifier do? Rectifier give you the voltage like this. Then after this we added a capacitor with the load, and then finally the output which we obtained was this output. So, finally what was our main reasoning to do this? We wanted a steady voltage, correct. So, this is how we can get a steady voltage. Okay. So, since these additional circuits appear to filter out the AC ripple and give a pure DC voltage is being obtained here. So, they are called as filters. Okay. Now, we shall discuss the role of capacitor in filtering. So, how is this capacitor used, or how is this capacitor being made so that it can filter up the works here, or basically this output can be obtained here. Okay. So, when the voltage across the capacitor is rising, it gets charged. So, these are all the basic concepts of capacitor. Okay. So, when the voltage is being applied across it, it gets charged up. Okay. So, the charging is being happening here. So, it gets filled like this. Okay. So, when the voltage across the capacitor is rising, it gets charged. If there is no external load, it remains charged to the peak voltage of the rectified output. Okay. So, it remains charged to the peak voltage of the rectified output. What is the rectified output? Peak voltage of rectified output, this is the peak voltage of the rectified output. Okay. So, it remains charged to the peak voltage of the rectified output. Now, when there is a load, let us say we add this load up here. So, when there is a load, it gets discharged through the load, and the voltage across it begins to fall. And so, the voltage keeps on falling across it, because this is being passed up to this what we can say resistor, or what we can say it to be a load. So, what happens in next half cycle of the rectified output? It again gets charged up to the peak value, and then again what happens is it get discharged because the load is being acted upon here. Okay. So, the rate of fall of the voltage across the capacitor depends upon the inverse product of capacitor C and the effective resistance RL used in the circuit, and is called as the time constant. So, what they are saying, that this rate of fall of voltage this is only being written here. So, it is written that the rate of fall of the voltage across the capacitor depends upon what? It depends upon the inverse product of what? Capacitor C and the effective resistance RL, fine, used in the circuit, and is called as a time constant. So, this is nothing but called as your time constant. Fine. So, this RC is called as a time constant. Okay. Next thing is to make the time constant large, the value of C should be large. Okay. So, if C is increased, then the value of time constant can be large. So, the capacitor input filters uses large capacitor. Okay. So, this is basically a filter. Okay. So, what does it say? It uses large capacitors. The output voltage obtained by using capacitor input filter is nearer to the peak voltage of the rectified voltage. Okay. What is the output voltage obtained? This is the output voltage obtained. The output voltage which is obtained by using the capacitor input filter, when we use this capacitor input filter, is very near to the peak voltage of the rectified voltage. So, they are just saying that, see, as you can see clearly that this is the peak, correct. This peak, if you see clearly, is at a location which is a little bit higher than the output voltage. So, that concept is being only explained here. So, if I just magnify this, you can see that there is some sort of a heap being created, and then there is a straight line. So, that is the only thing which is explained here, that this peak is a little bit higher than the output voltage. So, capacitor input filters use large capacitors. The output voltage obtained by using capacitor input filter is nearer to the peak voltage of the rectified output. Okay. This type of filter is most widely used in power supply. So, that is how you can obtain a constant source of supply of voltage or output. Okay. Fine. So, that is the end of your complete application of junction as a rectifier. Okay. So, what are all the concepts which we understood in this? First of all, we started with the discussion of your half wave rectifier, in which we understood that, let us say there is an AC voltage. What is happening for each of the for each of the half sinusoid which is in forward biased, the voltage is same. So, we get the same output, but when when it is reversed, it is basically in reverse biased, and therefore, the current is 0 there. So, only half wave is being rectified. We changed the circuit a little bit, we use a center tap transformer, and then we got a full wave rectifier, in which even though it does not depend upon the sinusoid which we are working upon, for each of the sinusoids a different diode will be working upon, and finally, the output is a half sinusoid movement which is going on. The next difficulty which was occurred was, it was okay, the polarity was same always, but it was not steady. So, to make it steady, what we did, we added filters. What is basically filter? If a capacitor is being added a parallel to the resistor load or the load, it is called as a filter. So, what is basically filter doing? Filter gets charged up, and this charge is being given to the load. Okay. So, that complete process leads to the steady current being evolved. Okay. So, either you can use a capacitor there, or either in parallel, or you can use an inductor there within series. Okay. So, that is how you can obtain this complete steady voltage. Okay. Now, so one of the application is given that it is most widely used in power supplies. Okay. Fine. So, that thing being said, let us now jump to the next topic, that is special purposes PN junction diodes. So, several different examples, so several different ways are there in which we use PN junction diodes, such as light emitting diodes, such as Zener diodes, etc. So, these all things will be detailed, will be explained in some brief. Okay. So, let us start with new subtopic, that is special purposes PN junction diode. Okay. So, in the section we shall discuss some devices which are basically junction diodes, but are developed for different applications. Okay. So, in this section we shall discuss some devices which are basically junction diodes, but are developed for different applications. So, what are the applications we will try to understand? First of all, let us try to understand Zener diodes. Okay. So, this is how a Zener diode is being formed, and this is the VI characteristic of a Zener diode. Okay. Okay. So, let us understand Zener diodes only first. So, what is a Zener diode basically? So, it is a special purpose semiconductor diode named after its inventor. So, what was its inventor name? Inventor name is C. Zener. So, that is how it name Zener came into picture. Okay. So, before going into this VI characteristic, let me just revise the VI characteristic which we know. So, we know it for a semiconductor device such that, let us say this is V, this is I, this is again V, and this is I. Correct. So, this is in your micro amperes, this is in your milliamperes, this is in your voltages, which is, let us say 0.2, 0.4, 0.6, 0.8, this is 20, this is 40, this is 60. Okay. So, it was something like this in the forward biasing, and this was something like this in the reverse biasing. Okay. So, that is how we understood this complete concept regarding this was in forward biasing. This was in reverse biasing. Okay. So, let us now understand whatever is written here. Okay. So, that was just a revision. So, now it is designed to operate under reverse bias in the breakdown region. Okay. So, it is designed where? It is designed to work under this reverse bias and in the breakdown region, okay, and used as a voltage regulator. So, we use it as a voltage regulator. The symbol for a Zener diode is shown in the figure A. So, this is how we make a Zener diode. So, this is the symbol for Zener diode. Zener diode is fabricated by heavily doping both P and N side of the junction. So, we dope even the P side also, we dope the N side of the junction. What is mean by doping? Doping basically is a process of the addition of the impurity particles into the semiconductor. Okay. Due to this, depletion region formed is very thin. It is 10 to the power less than 10 to the power minus 6 meters, and the electric field of the junction is extremely high. Electric field is approximately 5 into 10 to the power 6 volt per meter. even for very small reverse bias voltage of about 5 volts. Okay. So, the reverse bias voltage is very small, of even 5 volts we can obtain electric field which is very high. The IV characteristics are shown in the figure. It is seen that the applied reverse bias voltage V reaches the breakdown voltage Vz of the Zener diode. There is a large change in the current. So, as you can see, this is approximately perpendicular only. So, you can see even with a very small change in current after this Vz, the current will be increased in a very enormous amount. Okay. Note that after the breakdown voltage Vz, after this breakdown voltage Vz, a large change in the current can be produced by almost insignificant change in the reverse bias voltage. Okay. So, as we try to understand special purpose PN junction diodes, I would suggest you to remember that what is the basic criteria of its working. Okay. So, Zener diode generally works in your reverse bias condition. Okay. So, that being said, let me stop this discussion here only. In the next we will go on with the further discussion about Zener diodes, and then we can move on with one of the purposes or basically application of the Zener diodes as a voltage regulator. Okay. So, let me stop it here only. Thank you so much.